This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, in this hour, we're going to be talking about space, outer space, the exploration of space and what lurks out there in the farthest reaches of the universe. We're going to be bringing on two very special guests. The interviews were pre-recorded. The first interview is with Dr. Neil deGrasse Tyson, director of the Hayden Planetarium. You've probably seen him on a number of fantastic TV specials. And also, he's the host of the PBS Nova Science Now program. We're going to be talking about, well, some of the basics of astronomy, like how do you buy a telescope? What do you look for when you look in the heavens? And then second, we're going to talk about black holes. Perhaps one of the greatest secrets of the universe may lie inside the clutches of a black hole. And we're going to bring on one of the world's leading authorities on black holes, Dr. Fulvio Melia, who's dedicated his life to exploring some of the most extreme forms of stars in the universe. So we'll be talking about black holes. So there seems to be a buzz out there. More and more information is coming out about this great universe of ours. Recently, NASA released this rather earth-shaking report stating that there could be an alien life form in California, believe it or not, a new form of DNA that uses arsenic rather than phosphorus to create its DNA molecule. For the first time in history, if this result pans out, and of course, other scientists have to verify it, if this report pans out, it could be an earth-shaking discovery that will force us to rewrite all the biology textbooks. Even the definition of life may have to be changed. And it means that in outer space, when we look for signs of life, we have to be much more open-minded about what kinds of life forms can exist in outer space. And so once again, in this hour of exploration, we're going to be talking about some of the deepest mysteries of the universe and how you can be part of the great quest to explore the universe. Once again, our first special guest will be Dr. Neil deGrasse Tyson, director of the Hayden Planetarium, host of the PBS Nova Science Now series, and a frequent guest on TV programs. And the second guest is one of the world's leading authorities on black holes, Dr. Fulvio Melia, professor of astronomy at the University of Arizona, author of a number of great books about black holes, perhaps the most mysterious object in the entire universe. They are, in some sense, the ultimate Roach Motel. In other words, everything can check into a black hole. However, nothing ever checks out of a black hole. And that's what makes them so intriguing. They are perhaps the most fascinating, the most mysterious, and the most unexplained object in the universe. I mean, after all, if something falls into a black hole, where does it go? And what lies on the other side of a black hole? The first question for you, Dr. Tyson, is if you're a beginner and you want to look at the night sky via a telescope, but you don't want to buy a toy, but on the other hand, you don't want to spend thousands of dollars on the top-of-the-line telescope, what kind of telescope would you advise a beginner to get?
You know, I get that question maybe 1 billion times a month.
Okay, well, 1,000,000,001 now.
You're right. You don't want to get a toy because the toys, the cheap telescopes, no matter what they tell you on the box, the problem with the cheap telescopes is they're not only hard to use because they have bad mountings and you aim it at something and you just breathe on the telescope and the mounting shifts where the telescope was looking at and the image quality is poor. So just remove that from consideration. If you're worried about spending more on a telescope, then don't get the telescope at all. Just get a good pair of binoculars. Mm-hmm. And you can get a good pair for anywhere between $30 and $50. And binoculars are great because, particularly if you're a kid, you can do more than just look up with them. You can look horizontally with them. Right. And if you go to sporting events and that sort of thing. So binoculars have a tremendous utility that a telescope wouldn't have if you were never going to go beyond the entry level. So beyond that now, I would recommend a telescope. You'd have to spend, I think, at least $100.
Mm-hmm.
But consider that the telescope doesn't go out of style, and you'll have it for your entire life. So for things that you have for your entire life, $100 actually looks pretty cheap. And some better ones are up around $200 or $300. But what you want to make sure is that you have a sturdy enough mounting to keep a stable image in view. And telescopes get more and more and more expensive depending on how many bells and whistles you add.
Mm-hmm.
You get up around $1,000. Telescopes have computer-controlled pointing systems. Back in my day, we had to actually know where things were in the night sky.
Now you can be a dummy and simply
now just type it in, and the telescope, it has GPS controllers so that it knows where it is on Earth and knows where to point. So
you do nothing. You just sit it on the floor and it sort of like finds itself, right?
It makes coffee for you.
Yeah.
So basically, I would say there are a lot of camera shops that not only will be happy to sell you a piece of junk, your average good camera shop will also have the slightly higher level telescopes to sell you. And you want to make sure you have at least a couple of lenses, one to see large objects like the moon, others to see smaller ones where you need higher magnification. But so basically it's quite broad, and you might have specific needs. For example, maybe you don't have a car and you have to carry the thing yourself. Well, you stay away from the heavier telescopes. There's some simple needs that you might need have to accommodate simply based on where you're going to take the thing. But I can tell you this: if you happen to have a couple of dollars and you want to get a big, powerful telescope, the drawback is it may be so big that it's hard to take with you to places that you might otherwise be going, and then you don't end up using it at all. Mm-hmm. So try to find the telescope that's big enough, and telescope bigger is generally better. It's one of the few things in life where it's always true. Okay? Bigger telescopes.
We won't mention the other parts of life where it's not
generally are always better than little telescopes because they collect more light. Mm-hmm. If you collect more light, you can see dimmer things in the universe. Mm-hmm. So a simple telescope, a non-toy simple telescope, you can see the rings of Saturn, the moons of Jupiter, the weather bands on Jupiter. You can watch Jupiter rotate. You can see the craters on the moon. You can watch Venus go through phases. You can see that Mars is red and has ice caps on it. With proper filters, you can see sunspots on the sun in the daytime. You can see fuzzy splotches on the night sky, some of which are galaxies outside of the Milky Way. Others are just regions where stars are about to be born. So you can get pretty far on one of these first-level telescopes. But a larger telescope then will bring much more detail to those fuzzy objects, where you need more light to find out what you're looking at. And you'll see spiral structures and galaxies. You'll see centers of star clusters. With more light, you can see dimmer things. And the worst place to be for any of this is the city. Mm-hmm. You can make sure you've got friends in the country.
Yeah, right. Country
make sure you know the country mouse,
Right. So buy a telescope and a country house at the same time.
Yeah, there you go.
Now, there are two kinds of telescopes. One is the so-called spyglass or refracting telescope, this long tube. Mm-hmm. And then you also have, of course, the reflecting telescope of Isaac Newton. Mm-hmm. So how big which telescope would you recommend? And if you get a reflector, how big a mirror would you recommend?
I would say the largest practical sized, that is, kind you can just sort of pick up and take with you, a reflector, is going to be the 6-inch reflector. And it has a 6-inch diameter mirror at the back end, and light comes in, reflects off the mirror, bounces back to a device where you stick your eyepiece. And 6-inch diameter is a pretty good diameter for all things considered. Mm-hmm. But the reflecting telescopes are, because they're open-ended, dust can get in and you can actually drop things down and scratch the mirror. The other kind, the spyglass-style telescope, which is the more classically proportioned telescope that if you were to draw a telescope sight unseen, it's probably the one you would draw, the kind that pirates use. It's just this long tube with a lens at one end and a lens at the other end. And akin to what Galileo developed. That kind of telescope is a refracting telescope. Of course, it describes what the lens does to the light. It bends the light down to a focus. And my personal first telescope was a 2.5-inch refractor. And it's a nice sized telescope, and it can see all these things that I told you a moment ago. the rings of Saturn and craters and mountains and valleys on the moon. But it's a little more rugged. It's rugged. If you've got sort of rugged kids, for example, or if you yourself are a rugged adult, that's the kind of telescope you would sort of haul with you as you went out into the country.
And speaking about the rings of Saturn, during the Yankee game several years ago, it's a famous episode where the cameraman zoomed up and showed the rings of Saturn to millions of New Yorkers who had never, ever seen the rings of Saturn.
That is cool. Well, that's a testament to how good the zoom lenses are today.
Yeah.
Zoom lenses, I don't know the age distribution of your audience, but the old-timers will know there was a day before which there were simply no zoom lenses. And if you look at the old TV camera lenses of the past, they had a selection of lenses on a turret, and they would rotate that to bring a different lens into use. And all of the director's instructions never involved a zoom because there were no zoom lenses. And the number of optical elements to make a working zoom lens is so high, and the number of surfaces that the light passes through is so high that the true solution to that had to await computers to make that work. And so now if you can look at a wide-angle view of Yankee Stadium and then zoom into the rings of Saturn, you got a good camera on your hand.
Right.
That would cost much more than your telescope.
Yeah, much more. And the response was so enormous. So many people had never, ever seen the rings of Saturn. They called in. They thought it was a science fiction movie. And it was so great that the next day, they repeated it because the demand was so great during the Yankee game.
Yeah. Well, we need more of that. Just a reminder that sometimes you got to look up.
Which is, of course, hard for a lot of people.
Particularly city people, where if you look up, it's a pigeon's there or something. It's just not a natural thing to do.
You take your life in your own hands when you look up in the city.
And you might step in something. There's all kinds of hazards in the city.
Okay, now let's talk about your early life. Was a telescope there in your early life that propelled you to become an astrophysicist?
Yeah, I'm a city kid. In fact, I grew up in New York City, where the night sky, like I said, is a kind of a rare commodity. You don't even know it's there, really, most of the time. And my first telescope, my very first telescope was a Christmas gift from my parents.
Is that right?
And that was this 2.5-inch.
How old were you?
Refractor. I was 13. And
changed your life.
So it was not because it was my birthday, and I was just turning 13. And it changed. Well, no, I already knew where I was going. But the telescope empowers you to bring the vision to reality. Because I visited the local planetarium in New York, of course, the Hayden Planetarium. So I'd already been bitten by this cosmic bug, and now I had this hunger, and I had to feed it. And so that first telescope was a refracting telescope, and since I kept growing in my hunger and my thirst, I quickly outgrew that, and then I saved money from walking dogs.
Oh, is that right?
Yeah, in New York, as you may know.
A lot of demand for walking dogs.
A lot of lazy adults who own dogs in apartment buildings. You can't just let them out the back door. That would be a hazardous exercise if you live on the 30th floor of an apartment building. So you pay somebody, and they take your dogs out and you walk them. And in my day, I got 50 cents a walk, and a couple of times a day you'd walk the dog. I had it good back then. It doesn't sound like much money, but I didn't have to clean up after the dog the way people do today.
That's the name of the game, right?
Yeah, that's right. That's why they charge more for it, I think. But anyhow, I used that money to buy my next telescope, which was in fact a 6-inch reflector. And
so now you're with the big boys.
I was card-carrying amateur astronomer, and it came with a few lenses. I bought some more lenses, bought the solar filters, and I was ready. I was ready to take in the universe wherever it would get delivered. And I would haul the telescope to the roof of my apartment building, a 22-story apartment building in the Bronx. And I'm embarrassed to say that I was much older before I realized that the name of the apartment building I grew up in was called the Skyview Apartments.
Was that right?
Because it was just a word with no meaning to me.
Right.
While I lived there, and I looked back and I read the two words Skyview. Yeah, that's what I did up on the roof. So it's fascinating that yes, you can become an astrophysicist even if you are star-starved in the middle of the city.
And also, I understand that you have written your memoirs talking about this. Tell us a little bit about your memoirs.
Well, what happened was I kept getting so many questions about like what what I did when I was a kid and what I did in high school and college. I said, let me just write this down. Then I just hand him the book. I said, read this, call me in the morning. And so, yeah, in fact, my memoir, which in fact had a very first appearance a few years ago, is now in its new edition that just came out last year, at the end of last year. It's called The Sky Is Not the Limit. And it's subtitled Adventures of an Urban Astrophysicist.
That's a contradiction in terms, right? Like Microsoft Works. That's also a contradiction in terms.
I mean, urban astrophysicist. Well, you got to read it to find out how that contradiction gets resolved. But it chronicles part of what I think a reader might be interested in, how I got to where I am. But I don't then dwell on that fact, because I'm principally an educator, and what I do is I share the universe with people, but through the lens that I happen to carry as an astrophysicist, but also as a sort of public person in that realm. So a lot of them are sort of vignettes on how an astrophysicist sees the world around you.
Okay. Well, now let's talk about big telescopes, really big telescopes like the Hubble Space Telescope, which is currently orbiting the Earth. But if things go badly for the Hubble Space Telescope, it may plunge like a meteor, like a piece of space junk from outer space, and who knows, may land up in someone's backyard. What do you think about the accomplishments of the Hubble Space Telescope, and do you think it should be allowed to fall back to Earth?
That's a very rich question, and let me address it a couple of ways, but I'm happy to be brief if you have other topics as well you want to cover. The Hubble telescope, as you may know, just celebrated its 15th anniversary, and there is no telescope that's orbiting the Earth that has that longevity, and that longevity came about, and the belovedness of the telescope in part came about because we were able to fix the thing, to service it, to improve it. As electronics and technologies advanced, you go up and swap out the detector, that's the business end of the telescope, and put in a new one. Because really, a telescope is simply a bucket to collect light. And what you put at the focus end, that's up to whatever is the state of your technologies. So the fact that it was serviceable by the space shuttle, by astronauts, meant that the accomplishments of Hubble could accumulate in our hearts and minds far beyond the normal life expectancy of a spaceborne telescope. And so whole generations of people grew up knowing Hubble as their favorite thing through elementary school into high school and into college. So that in part accounts for the love affair we all have with the telescope, not to mention the striking images that everyone now has as their screensaver for their computer. If you look at the productivity of the telescope, in scientific terms, as you know, we measure this by not only how many research papers came out of it, but how many citations those research papers received, which is, on the other end, a measure of how influential that research was. And the Hubble telescope, hands down, is the most fertile scientific instrument in the history of science.
Is that right?
That's correct. If you combine both of these factors, number of papers published and number of citations received, there is no comparison. And so that's extraordinary. I mean, and you wonder, how could anyone say, let's deorbit it? Well, the reason why that came up is there are other telescopes that were on the books, that were ready to be launched and ready to go up, and will go places Hubble does not go, that is, scientifically, will tread ground that Hubble cannot tread. And so you're left with this fascinating dilemma. There's the bird in the hand, the working telescope that you know is successful and will continue to make discoveries, and this new technology that's going to go up with a new kind of telescope. By the way, the launch vehicle might blow up on the pad, for all we know, right? And then it's gone. You got nothing, right? Meanwhile, Hubble is deorbiting. So there are complex sort of funding, scientific, and political issues that surround when you turn off an instrument and when you turn on the next one. So right now, up to the minute, last I checked, the new head of NASA, who, by the way, has all the right pedigree to get NASA out of its doldrums and take us somewhere interesting. He's a physicist, he's an engineer, he managed companies, he's got the spirit of a young person, he's got the maturity of an old person, He's got everything. He came from Central Casting.
I see.
Who do you need for NASA to take us in? His name is Michael Griffin. But anyhow, right now he responded to these sort of battle cries of the turning off Hubble, and he says, yes, let's look into what it takes to save Hubble. But in a limited budget environment, I have to pull money from other places. And so he reached to some of these other telescopes and pulled away the money, not to cancel those missions, but to delay them, which is a softer consequence, right, than actually canceling them. Well, now we have the scientists who are part of those missions complaining, saying, no, this is bad. And so this is the politics of a limited budget.
Well, why don't they take a little bit of money from the International Space Station, which nobody wants, and even President George W. Bush has not expressed much enthusiasm for this bathtub in outer space called the International Space Station, and maybe take a little bit of money from the space shuttle. They cost enormous sums of money for the manned space program.
There are two ways I can answer that. One of them is just since we know we want to go beyond the shuttle and the space station in the new vision for space exploration, why not just turn off the switches now? Just abandon them in place or give them to the Europeans, whatever. The problem is there's a lot embedded in that sort of rolling ball. We have international commitments to complete the space station because we have international partners in this exercise. So the recommendations that exist in the new vision for space exploration, now a year and a half old, those recommendations say we will phase out the shuttle, phase out the space station. In big government, you can't just turn off a switch. You have to you need an exit plan. So you turn them out. I mean, you phase them out. And while you phase them out, you phase in the rest of this vision. And so they are now on a phase out trajectory, a phase out plan to have all the budgets go to zero while we finish the space station. And once the space station is done, the shuttle gets retired. So that's a good thing. But you just want that to happen even faster.
Yeah, it's a $100 billion space station, and no one can find a mission for it. What's it doing up there?
Well, that's another interesting
that's a whole other
history.
Question.
It was born out of a whole other era. It was conceptually born in the Cold War. We don't want the commies with space stations over our heads, right. Kind of thing. And then you kind of buy into it, and then it's kind of there, right? And so that's a complicated political history. I'm happy to say that the new vision for space exploration does not have that depth of politics driving it. There's exploration driving it. There's economics driving it. The goal and the hope is that it stimulates industries in ways that the stimulation of flight, the investment in flight stimulated associated industries. So there's some ambitious plans for it that don't derive from political whim, which I think can be the strength of any project.
Okay. Now let's talk about the search for life in outer space. The Mars rovers have been roving over the surface.
Let's first talk about the search for intelligent life on Earth.
Oh, well, there is none. We know that.
Okay.
That's a settled question.
That's a whole other program, all right? We'll save that one. But go on, I'm sorry.
Okay, well, Mars, right? We've had this fascination with Mars, and Spielberg and Tom Cruise
this summer
are going to scare the pants off us with, War of the Worlds. And the question is, well, have we learned anything new? We see pictures of rocks. We see indications of maybe water once floating on the surface of Mars. Anything surprising that caught your attention concerning the Mars rovers?
Well, as you know, the Mars has twin rovers, six-wheeling on its surface right now as we speak. And they're on opposite sides of the planet, so that there's always one in view that we can talk to and get the data from. And there's always one in sunlight. So that's a clever way to explore the planet. These two rovers. Now, I am an astrophysicist, not a geologist or a geophysicist. So there's a limit to how excited I can get by just looking at rocks.
A bunch of rocks, right?
Right. So, but in all respect to them, they get into their rocks. If any of us have known a geologist, their home is filled with rocks that they found out in the valley and in the mountains and in the, so among this, given this fact, the subset of the rocks that I'm curious about are those that could have only formed in the presence of liquid water. Because the goal of the astrophysicist is not tell me what kind of minerals are there, unless those minerals impact or affect the kinds of questions we want answered about whether Mars once had liquid water. Because on Earth, where there's liquid water, there is life. So we have this, you can call it a bias, but I think it's an okay bias, that the search for life as we know it involves the search for liquid water. So NASA has this mantra, follow the water. And so these rovers had, as one of their primary missions, look for rocks that may have been formed in the presence of water. And in fact, they found them. So we're jumping for joy at this. And so that helps us shape the next mission to Mars, because we know there's no water on the Martian surface. Where did the water go? It's a big mystery. And most experts in this effort believe the water sunk down into the surface and has now formed a kind of permafrost. And so your next round of missions to Mars are going to have to be able to dig. And so we're going to go to places where we think the water is shallowest and start digging. And so that's the role of these missions in the big picture for our search for life on Mars.
And speaking about digging, in the near future, NASA wants to send a space probe to one of the moons of Jupiter, Europa, which may have a liquid ocean underneath the ice cover. And NASA does have plans. I've seen some of the animation for it, to dig right through the ice of this moon of Jupiter to access the ocean and perhaps one day send a submarine down there. What are your thoughts? Is that a long shot concerning a liquid ocean under the surface of the ice cover of a moon of Jupiter?
That's currently my favorite plan in the works right now. It's still just sort of being sketched. There's no sort of hardware being committed to that idea yet. But in the minds of creative people, the hardware is getting committed. They're trying to figure out how to do this. There's this moon of Jupiter. By the way, the whole Jupiter system, and it's got dozens of moons. I have lost count. One of those moons is one of the largest among them, discovered by Galileo. In fact, it's called it's called one of the Galilean moons. It's called Europa. And it is way outside of this zone around the sun where the temperature is just right for liquid water. Earth is in that zone. We're not too close. We're not too far. We're just right. It's Goldilocks. We're just right to have liquid water. You go to Jupiter, you expect everything to be frozen. But you know something? The ice on the European surface is, yes, it's frozen. There are cracks in the ice.
And that concludes our interview with Dr. Neil Tyson, leading African-American scientist, director of the Hayden Planetarium in New York City. And if you want a copy of today's program, call the Pacifica Program Service at 1-800-735-0230. That's 1-800-735-0230. Stay tuned now for the second half of Exploration as we talk about black holes with Dr. Fulvia Melia, one of the leading authorities on those mysterious objects in the universe called black holes. So stay tuned now for the second half of Exploration as we leave the fabric of space-time and enter the world of Einstein, the world of black holes, with Dr. Fulvia Melia. Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. And this is the second half of Exploration. In the first half of Exploration, we conducted an interview with Dr. Neil Tyson, leading African-American scientist, director of the Hayden Planetarium, and author of numerous books on astronomy. Well, in the second half of Exploration, we're going to continue our discussion about exploring the universe with black holes. Our special guest today is Dr. Fulvio Melia. He's the author of a book called The Edge of Infinity, and we are talking about the mysterious objects in the universe photographed by the Hubble Space Telescope called black holes. Well, black holes are so massive that even light itself cannot escape. In fact, when we photograph these black holes, we actually photograph the swirling disk of matter and energy and stars that swirl around the black hole. One of these days, perhaps one of these days, we'll be able to get right up close and photograph the event horizon, a sphere surrounding the black hole. And if you were to go through the sphere, it is the point of no return. And believe it or not, in our own Milky Way galaxy, at the center of our own backyard, the Milky Way galaxy, there's a gigantic black hole. It weighs about 2 million times or so the mass of our sun. And of course, there's ample speculation about what happens if you were to fall into a black hole and wind up on the other side. I should also point out that if you want to find out more about black holes and what could possibly lie on the other side of forever, get a copy of my books, Physics of the Impossible and also Parallel Worlds. These books go in much more detail than what we can cover here in this interview. Specifically, we talk about whether or not there's something on the other side of a black hole. Is there a white hole that connects a black hole? So when that matter falls into a black hole, it's spewed out the other end in terms of a white hole. And doesn't the white hole look like the Big Bang itself? In fact, there are some physicists who stick their neck out and say that perhaps there's another universe on the other side of a black hole. So when matter falls in, it blows out the other end, just like a Big Bang with the creation of another universe. That, of course, is still speculation, but for more details, consult my books, Physics of the Impossible and also Parallel Worlds. So once again, let's now continue our interview with Dr. Fulvio Melia of the University of Arizona, one of the world's authorities on black hole physics. The first question for you is, how did you first get interested in physics and astronomy?
Well, I actually grew up in Melbourne, and I don't know if all of your listeners have had the opportunity of visiting the Southern Hemisphere, but looking up at the sky from the Southern Hemisphere, one gets quite a different view than from the Northern Hemisphere. The Milky Way, for example, is very easily seen, and it stretches from one horizon to the next, and it fills the cosmic vault. And when I was small, I remember almost every evening just going outdoors and just looking at the stars in the Milky Way for hours and hours and hours. And I would say that that's probably what started me off. With that, of course, comes the natural curiosity of how things work and what these objects are, and one is led, I think, in most cases, to a study of physics, and that's what got me into physics and astronomy, I would say.
And Arizona is one of the world's leading centers for astronomical research, I understand. So what is it like to be in Arizona versus being in New York City, to be able to look up at the night sky and see the Milky Way, and also to be at the very forefront of telescope technology?
Well, that's the interesting comparison, of course, because even though I usually tell my friends, especially the ones overseas, even though we belong to the same country, the southwest of the United States is really very, very different from the Northeast, as I think everybody realizes. Here in Arizona, the skies are almost always clear. It's not a coincidence that many of the national and now the international telescope facilities are being built here. We get very little cloud cover during the year, so going out in the evenings, whether using a telescope or not, presents quite a glorious experience. It's a wonderful opportunity to feel the magnitude of the skies and the objects there. And of course, for research, especially for the observers and people who build instruments eventually placed on the telescopes with which these observations are made, there are very few places on the planet better than this to do studies such as this. The clarity of the skies and also the access to objects not only in the northern hemisphere, but those approaching what one would see from the southern hemisphere. Of course, Earth's rim prevents us from seeing all of the portion of the Milky Way that would be accessible from the south, but nonetheless, during a portion of the year, we can still see the center of the galaxy, for example, which is close to the southern horizon for us here in Arizona. But other than the skies here, the only other place that would present a comparable opportunity for studying these objects would be from countries such as Chile, which of course is way down south. So as far as we here in the United States are concerned, unless we want to travel to South America, this is probably the place to do this type of work.
And also, tell us a little bit about how stars die and the formation of black holes.
Right. Well, this, of course, is an ongoing investigation. We think we understand some pieces of the puzzle. Not everything is known. It's quite a long story. Black holes can actually form in several ways, and it's not clear that the supermassive objects that we see in the nuclei of galaxies form through the stellar process of life and then death. They may have formed in other ways, and we may come back to this in a few moments when we talk about the genesis of these objects early on after the Big Bang. But in terms of the smaller black holes, like the ones like Cygnus X1, for example, these are the objects that we think weigh perhaps 10 to 20 times as much as the Sun. As far as these objects are concerned, most of them are produced when a very massive star, and by very massive we mean something, an object that weighs anywhere between 30 to 50 times the mass of the Sun, burns its nuclear fuel rather quickly, it turns out, because the more massive the object is, the faster it burns the fuel, and then eventually loses that internal support that prevents it from collapsing to the middle. It's the heat generated from nuclear burning that preserves the star during the main part of its life, like the Sun is now. And at the end, when that nuclear fuel is burned to heavier elements such as carbon and eventually to iron, the heat generation stops and the material can't support itself anymore and collapses into the middle, at which point a supernova explosion ensues, and the remnant, depending on how massive the original star was, can sometimes be a black hole with a mass somewhere between a couple of solar masses and 10 to 20, as I said earlier. So the vast majority of black holes about which we know, and there are some billion of these in the galaxy, probably formed in this way. But there is another class of objects, like the one at the center of our galaxy and the center of many other galaxies, such as the Andromeda galaxy, our sister galaxy. These objects have a mass anywhere between 1 million to several billion times the mass of the Sun. And although some of them may have started as seeds from supernova explosions a long, long time ago and eventually have grown to the point where they are now, it's not clear that all of them could have formed that way. And the reason I say that, and this would lead into another part of the story, the reason I say that is that we now have very, very strong evidence that at least some of these supermassive objects were formed only 700 million years after the Big Bang, much, much earlier than the formation of galaxies and much of the structure that we see in the universe today. So it's starting to look like there was some other mechanism, some other process that led to this early collapse and this catastrophic creation of very strong gravity surrounding these objects, which probably also then acted as nucleation sites that attracted other matter towards them, and that matter, we think, in many cases, may have led to the formation of galaxies. So the odd thing now is that we may actually owe our existence to the formation of these supermassive black holes, because they may have been the seeds that created galaxies, which then, of course, created stars within them and planets and life and so on. So it's quite a long complex story, and we don't know all the details yet, but some of the pieces of the puzzle are starting to emerge in that there definitely appear to be several classes of these, and one class having to do with the supermassive object somehow had a genesis much, much earlier than we thought before, and how they formed is not entirely clear yet.
Well, I have a question that many young people ask about black holes. First of all, black holes suck in everything. Even light itself cannot escape. In some sense, they're the ultimate roach hotel. And the Hubble Space Telescope has photographed the black holes eating up whole star systems. So in other words, things check into a black hole, but nothing ever checks out. Well, then the question is, well, a black hole should be invisible. Even light itself cannot escape from a black hole. Therefore, a black hole should be invisible. And yet we have the Hubble Space Telescope taking photographs of perhaps hundreds of black holes in outer space. And so then the question is, how do you photograph something that is invisible?
Right. This is what's really generating much of the excitement these days with theoretical astrophysicists and, of course, the physics community in general. What telescopes that have been built up to this point have seen so far is not really the black hole itself, but what they see is light produced by matter falling into the black hole. Their resolution is not yet good enough for them to make an image of the black hole itself, the event horizon, which is the surface beyond which nothing can escape, including light. So if we really could see the black hole itself, what we would see is a dark shadow in front of a curtain of light. The curtain of light presumably would be produced by matter behind the black hole relative to us, and the black hole would absorb all of the light produced behind it or redirect it away from our line of sight, because gravity can bend the path of light, and so we would see a dark shadow. That's what a black hole would look like if we had a camera with such clarity, such spatial resolution that we could see detail down to that size. It does look like by the end of the decade we may have the capability of actually forming such an image. But for now, telescopes such as Hubble and Chandra have not been able to do that yet. So instead what they show us is images, or what they produce is images of matter falling into the black hole from larger distances much further away than the event horizon itself. Both have done spectacularly in this regard, though. Both Chandra, the X-ray telescope, and Hubble have each produced a very deep image of certain patches of the sky. By deep, we mean that there were patches in the sky, such as one in the constellation of Ursa Major, where there are very, very few objects within our own galaxy inside of that patch, and so it's like looking through a relatively open window to much distances much further away than objects within our galaxy. And what they were able to do by staring at these patches was to collect light from objects some 10 to 12 billion light years away. In other words, objects that were producing this light only 7 to 8, 900 million years after the Big Bang. And what they see when they look at these patches is very bright objects, either X-ray objects or ultraviolet or infrared objects in the case of Hubble, objects that number as many as 500 within a region only the size of the full moon. So if you can imagine with your eye looking at a part of the sky that has the size of the full moon, within such a region, these telescopes have been able to produce images of as many as 500 of these objects. And these objects are so far away, they're so bright, that the only way that they could produce this much light is if they're black holes absorbing matter from their environment and converting gravitational and rest mass energy into light. So we believe that when we look at these patches, most of the objects that we see, most of the 500, must be supermassive black holes at that distance in the universe. And what's interesting is that when one extrapolates over the whole sky, these numbers correspond to total numbers of some 300 to 400 million such objects. And we know that that's not all that's there, because that's what we can count. That's what we can see. But some of these objects are probably also obscured by dusty matter falling in towards them, and so it's not clear that we're seeing everything. So the best that we can say is that there must be at least 300 million of these supermassive black holes spread throughout the cosmos. Chandra, of course, has gone on and done even much better than that. It's allowed us to look at the supermassive black hole at the center of our own galaxy with even better clarity because it's much closer than the others. It's only 25,000 light years away compared to the 12 billion light years of many of these other objects near the beginning of the universe's life. And because this object at the center of our galaxy is so close, we've been able to study it with Chandra and now other instruments as well. The European Space Agency has its own X-ray telescope called XMM Newton, which has done similarly spectacular studies of these objects. But with Chandra, we've been able to see the X-rays produced by the black hole at the center of our galaxy with enough resolution that we can actually place the source, the location of the emitting plasma, within a region no bigger than the distance between the Earth and the Sun. In addition, this object seems to explode roughly once a day, producing a flare of X-rays. The X-ray intensity during these events goes up by anywhere between 30 and 200 times what the intensity is during the quiescent state. And so for a couple of hours, the black hole at the center of our galaxy shines much, much brighter than it otherwise does. And what's intriguing now, and these are the latest results that haven't even been published in the literature, what's intriguing now is that there is very clear evidence that during these events, we can see a periodic pulse. It's like the heartbeat of this object. There's a periodic pulse that occurs roughly once every 20 minutes. The natural interpretation for this, and again, it hasn't been published yet, so we have to look at this more carefully and make sure that we've ruled out all the other possibilities. But the natural interpretation is that what we're looking at is a phenomenon associated with X-rays being produced in a region orbiting the black hole within a distance only 3 to 4 times the size of the event horizon. So although we can't see the event horizon just yet with Chandra or Hubble, nonetheless, we're seeing a phenomenon associated with a mission that's occurring only 2 to 3 times the size of the event horizon. It's similar to what would happen if you imagine putting a searchlight on a planet and being in its focal cone only when the searchlight is pointing towards you. And so you would see a pulse every time the planet goes around the sun, which would then lead to a periodicity or a period of 1 year in the case of the Earth, because that's how long it takes the Earth to go around the sun. So it's a similar phenomenon with the black hole at the galactic center. We see this pulsation roughly every 20 minutes, and so we interpret that as being part of the plasma in orbit around the black hole, and the distance that corresponds to that period is about 3 times the size of the event horizon. So these are some of the most exciting things that are happening now as we speak, and the prospects will get only better as time passes and Chandra and XMM continue to look and discover additional activity, and also with the next generation of telescopes in the pipeline now.
Now, everyone asks the question, what happens if you fall into a black hole? No one's ever done that, of course. But could you explain some of the distortions of space-time that occur if you were to fall into a black hole and someone were to observe you falling into a black hole from a distant planet?
Right. And the answer to that, of course, depends, not surprisingly, on how massive the black hole is. What one would see falling through the event horizon differs depending on how massive the black hole is compared to the mass of the object or the body falling in. It turns out that for a massive object like the one at the galactic center, which we now understand has roughly 3 million solar masses worth of material contained within it, falling through the event horizon of an object like that, a person would actually not see very much, would actually not feel very strong effects on his or her body. There would be other distortions to the light, but we'll come back to that in a moment. The point is that what happens physically to matter falling through the event horizon depends on how big the object falling in is compared to how big the event horizon is. And the size of the event horizon scales with the mass of the black hole. So, for example, if the sun were to shrink down to the size of a black hole, its event horizon would have a radius of only 3 kilometers, smaller than a city. Whereas the black hole at the galactic center has an event horizon with a radius about 1/20th the distance between the Earth and the Sun, which is much, much bigger, of course, than 3 kilometers. And it's the difference or the comparison between the size of the event horizon and the size of the object falling in that determines how much physical damage, if we can put it that way, is done to the object falling in. So because our body is so small compared to the size of the event horizon of the black hole at the galactic center, we could fall right through and not feel very much physical damage. We wouldn't get distorted or pulled or stretched or compressed. We would be able to pass through the event horizon, and then other catastrophic events would ensue, I'm sure, after that. But the process of falling in wouldn't do damage to us. On the other hand, if we were to fall through a smaller black hole, like the sun, again, if the sun were to be compressed to 3 kilometer size, then our body would get stretched at first, pulled apart, and catastrophic damage would follow. We would be disintegrated, and only the atoms and molecules would fall through. So the physical damage is different depending on the size. And a good analogy would be compare standing on the surface of the Earth, where the surface of the Earth, even though it's spherical, looks flat to us because it's so much bigger than us, and then standing on the dome of a cathedral. The dome also is quasi-spherical at the top, but because the size of the sphere is much smaller compared to the Earth and much closer to our size, we feel the curvature of the dome much more. And so that's the analogy. A small black hole, because of its greater curvature relative to us, would do more damage to our body falling through than a big black hole does. Now, that's as far as physical damage is concerned. But what we see, though, would be less dependent on the size, and there would be significant distortion to the light path progressively as we get closer and closer to the event horizon. So light, because of gravitational redshift, meaning that photons have progressively less and less energy, not speed. The speed of light is always the same, but the energy of the photons decreases relative to us at infinity as they get closer and closer to the event horizon. Because of that decreasing energy, we have greater and greater difficulty seeing the light. Eventually, as the as the light reaches the event horizon, it's lost all of its energy relative to what we see, and so we wouldn't be able to even detect the light anymore, even though it would still be coming out until it passes through the event horizon, and then beyond that, we wouldn't see it anymore. But as we fall in, because of this effect, we would tend to see primarily light concentrated closer and closer to the zenith angle, right above our head. So as we get closer to the event horizon, we see a progressively smaller cone of light from the rest of the universe until that point when we cross the event horizon itself, and only the light coming directly down would be visible to us. And so we would see these significant distortions because of the light bending and the gravitational redshift. And when we cross the event horizon, then of course nothing can go back out, so we can't communicate with the outside world, but what we would see is only light falling directly inwards towards us.
Now, Stephen Hawking made headlines a few months ago concerning the information problem. That is, if you take the Encyclopedia Britannica and you were to throw it into a black hole, all that information, said Stephen Hawking, would be permanently lost because it can't be retrieved. However, he took back that position a few months ago. Could you explain to us exactly what is this information problem that Stephen Hawking was addressing that made the front pages of so many newspapers?
Right. This is a very important problem, of course, because it's right on the interface between quantum mechanics and general relativity. And as you know yourself very well, Michio, there's this significant conflict between what quantum mechanics says and requires and what classical general relativity says and requires. They're almost at two opposite ends when it comes to this question of information loss and how one treats the force and so on. So in quantum mechanics, information cannot be lost. But in general relativity, which is a classical theory, and these issues hadn't come up at the time when general relativity was being developed, when an object falls through the event horizon, as we were saying before, all the information that it carries with it, the number of protons, the number of electrons, any geometric configuration, past history, whatever it has, is never accessible again to the outside world, to the universe outside of the black hole. And so that's the paradox, or the conflict, I should say. It's not really a paradox, but that's the conflict between quantum mechanics and general relativity.
Well, I'm afraid that's it for Exploration. Once again, our first special guest was Dr. Neil Tyson, director of the Hayden Planetarium in New York City, leading African-American scientist. The second special guest was Dr. Fulvia Melia, chairman of the physics department at the University of Arizona and author of the book Edge of Infinity. And be sure to go to my website, www.mkaku.org, mkaku.org, where it lists my complete book tour, because I will be traveling around the country signing books and talking about Parallel Worlds, the new paperback edition of my book, the latest book to discuss cosmology, string theory, higher dimensions, time travel, the birth and perhaps the end of the universe. Good day.
Friday, July 3rd at 7 o'clock p.m. You're invited to join us live on Full Circle. People nationwide will be beginning their 4th of July weekends, kicking off on the 3rd with barbecues, fireworks, and cargo shorts. As many prepare to celebrate the independence of America and commemorate freedom, Full Circle is taking a moment to slow down and talk about incarceration. The issue of incarceration and treatment of prisoners is paramount to a nation that fancies itself a world leader. We'll feature conversations with formerly incarcerated individuals as well as people who work with and serve men and women in prison. You can listen as we visit the issue of incarceration and freedom on Friday, July 3rd. Full Circle is produced by the First Voice Media Apprentices and airs live at 7 o'clock p.m. every Friday night on 94.1 FM KPFA and online at kpfa.org.
Max Blumenthal is coming to the Bay with his fierce new book on Gaza. In the 51-day war, Max audaciously takes clear-eyed, on-the-ground journalism into the deeper realm of geopolitics. The author of Republican Gomorrah and Goliath, Max was in Gaza, Palestine, and Israel throughout the recent ultra-violent assault on Gaza. On Wednesday, July 1st, 7:30 p.m., he'll be at First Congregational Church, 2345 Channing Way in Berkeley. Philip Maldery will host this KPFA benefit. There is wheelchair access. Tickets are at brownpapertickets.com and supportive bookstores. Find more information on the KPFA website. For Max Blumenthal, July 1st, The Truth About Gaza, Past and Future.